Okay. Okay. So we were discussing yesterday about inverse problems for nonlinear hyperbolic equations, or like wave propagation, and I mentioned several works related to that. This is by no means a complete list. I mean, this is. So you already had a little bit about nonlinear acoustics from Young. I will briefly remind you of that. But before doing that, what we were considering before was the source to solution map. I don't know whether you remember, but so this was the source to solution map. So you have a source here, and you map it to the solution in the neighborhood where you are making the observations. And the support of F is also contained in this neighborhood. It can be as small as you want, or as large as you want, as you have. And so, but also it's important to consider inverse problems for when you have a boundary. We did consider that for elliptic equations in the first two lectures for the Calderon problem and Gelfand problem. So I'm going to look at the case when you have boundaries, which is certainly more complicated. Because for the case of boundary, when you send waves, you have a source of waves like here, they will reflect. And if the boundary is more complicated, it will have very complicated behavior. So before we define the light observation set. So here I'm going to define the boundary light observation set. So you have think of M as a domain cross time. Let's say the picture is in 1+2 dimension. And then we have a set S here, which will be the set of sources. So this point is in S here. And we make the observations at the boundary. So in a part of the boundary, so this is partial data, part of the boundary here. And we denote this, the data that we're going to have will be the analog of the light cone starting at the point Q. This is the point Q here. You take the light cone, but in this case will reflect. Right? And you intersect it with the region of observation U. Okay? So this is, and we're going to show this is, I want to state it more precisely in a minute, but this collection, the intersections of these reflected cones intersected with the region of observation determines the conformal structure, meaning the metric. Remember, this is a Lorentzian metric of signature minus plus plus plus. And you can only, because we're taking the light cones here, this is invariant and the conformal changes. You take a multiple, these are the points where the metric vanishes. Like in Minkowski metric, this is the light cone. So we can only consider at best a conformal class. Somebody was asking me yesterday about whether you can recover the conformal class geometrically. And this is the case if you have other observations. Let me mention this. I jumped over this yesterday, since somebody asked me about this here. So this was a light observation set, right? You take the light cone. The reason why we can only recover the conformal class is because the light cone is where the metric vanishes. Right? This is what the propagation of light is. But you can consider other, instead of light, which propagates at the speed of light, of course. This is propagation at the speed of light. You can consider neutrinos, which are in abundance in the universe, which have a speed of propagation is lower than the speed of light, but very close to the speed of light. And they do not interact much with electromagnetic fields and can be detected and is produced actually in sufficient quantities all around the universe. And this is a particle that one can use, and they come, for instance, for supernova. The supernova is exploding death of a big star, and supernova releases photons, light, and neutrinos in great numbers, and the speed is very close to the speed of light. And it's not on the light cone, so you break the conformal invariance. Okay, and the neutrino cone depends on the motion of the dying star. This is when the supernova is dying. The light cone does not. So this is, the theorem is that you have already determined the conformal class from the light observation set. When you measure these neutrino cones, you can also recover the conformal factor. So this is the picture. This is the light cone, and this is the neutrino cone, and this is moving with the star that is exploding. So you know both, you can recover the metric itself. Okay, so these are measurements, different kinds of measurements. This is light, and these are neutrinos.
What's the time scale between the supernova and the neutrino explosion?
Actually,
How old is this?
well, I don't know right now. It's very close. It's very close. But the velocity is very close to the velocity, and this is moving also with, so they're released earlier than photons. So the catching up time is not, they catch up with the photons pretty much. Okay, so this is, somebody asked me this question. I was not going to mention it, but so now we come back to the case of boundary. So I'm going to take as the reflected light cones starting at points in the interior. And then you can recover the conformal structure of the set S that where you have your sources. So the reflection at the boundary is governed by Snell's law. So you have a null geodesic, that means photons, propagation in the light cone, and they hit the boundary, and they reflect following angular incidence equal to angular reflections. So you continue the curve as a broken geodesic. So this is a geodesic, and then hits the boundary, and then reflects. So in order to have just, this reflection can be very complicated if the boundary is not convex. So suppose you have some set like this. Oops. Oh, thank you. Okay, so if the boundary is very complicated, suppose then you can have very complicated behavior here. The geodesic, some places hit transversally, but these geodesics here stay outside. So, and you can have very complicated behavior here, and so on. So I'm going to assume that the boundary is strictly convex, so that the light cone hits the boundary transversally. Okay, so to simplify, I mean, this is will be a good problem to consider the non-convex case. And this is what is said here. It's called null convexity. It means all the geodesics, null geodesics, the ones starting on the light cone, hit it transversally. Okay? And so where they find the light cones using the broken null geodesic. So this ray and Brock's here in this following Snell's law. And we intersected again with the region of observation, but I don't consider all the reflections. And the result, to state it more precisely, suppose you have a Lorentzian manifold. Remember, Lorentzian means as the signature, this is a matrix of signature minus plus, let's say in dimension 3 plus 1, plus, plus, plus. We have a time, notion of time, and sources in the interior, where this is compact, and we observe in an open subset of the boundary, like in this picture here. And we assume some condition which is actually necessary. There are counterexamples if you don't assume this condition, that the broken light cones intersecting with the region of observation are different for different points. Because you can have a point away that sort of the reflections become the same. I will give a picture in a moment, counterexamples. So you have the smooth manifold U. This is the set of observation, the open set on the boundary. And you have the intersection, again, of the light cones, broken light cones, intersected with the region of observation. You can recover uniquely the set S, the topology of the set, the differential structure, and the conformal class of the metric. That means a metric up to a multiple. Again, we cannot recover the metric itself, except if you consider other information. Okay, so again, this in the case that you have a product, the product situation where you have a Riemannian manifold here, positive definite cross time. So this of this form, minus dt squared plus h. This is independent of t. This case, null convexity is just a strict convexity of the boundary here. It's the same. And the counterexample, why do we need this condition, is that you can have 2 points, Q1 and Q2, where it depends on the region of observation. We are observing here. Then the broken light cone is the same in both cases. Q2 and Q1 intersected with U. Here, it's just this. Because this, you take the cone here, and then it's exactly the same as the other one when you intersect it with U. The broken cone here will leave U. This will leave U eventually. So S1 and S1, U2 are indistinguishable. In this neighborhood, of course, they are distinguishable as you consider the whole boundary. Okay, so what we are going to do is take the Dirichlet to Neumann map. So in general, you take Dirichlet data supported in some open subset of the boundary, and you measure the Neumann data in other subset. And the important case is when these are the same. You're making the measurements in the same set. And then from the point of view of singularities, that is for the strict convex case, there are very good theorems on propagation of singularities. So singularity propagate along broken geodesics. Let me point out here a very general result of Melrose and Sjostran in the late 70s, where they consider non-convex boundaries. This is this case. So there is an optimal propagation of singularities result. So one open problem is to consider a non-convex case. But this, of course, is more difficult. I just want to present the simplest case here. Okay, so let me look at one result that one can obtain. Remember, X involves position and time. So you have a product here, and this is the wave equation associated to the Lorentzian metric depends on time. Metric depends on time. That's the point of doing all of this. And here this function A depends on x, depends on position and time, and you're given boundary data in the lateral boundary here. So it's supported on the lateral boundary, and it's 0 in the past. And the inverse problem one can look out is to determine both the metric G. You can think of the metric G as the sound speed, depending on time. And the coefficient A by measuring the Dirichlet to Neumann map in this case. So you map Dirichlet data to Neumann data, which these are supported in sufficiently regular for some interval of time across the boundary. So if they're equal, then there exists a diffeomorphism so that this is the identity of the boundary. Remember, there is the same obstruction that we have for the elliptic problem. So diffeomorphisms that are the identity of the boundary leave the problem invariant. And then there is because of the conformal invariance of the boundary light observation set, not of the equation, there is a function so that vanishes at the boundary, and the normal derivative vanishes at the boundary, so that in this neighborhood, one metric is the conformal multiple of the pullback of the other. Remember, conformal, this is the pullback, sorry, means the differential of, in terms of matrices, differential of psi composed with G, composed with differential transpose, composed with psi. That's called the pullback of the metric G. And this is a conformal factor, a multiple. Remember, we can only recover from the boundary light observation set a multiple. You would like to have this multiple to be 1. And that would be the case if we can show, but we can show this factor e to the minus beta satisfies the wave equation. We can show that if you have a solution of the wave equation with boundary data and the normal derivative to be 0 on the lateral boundary, this unique continuation result then implies beta equal to 0. In that case, e to the minus beta will be 1, and so that will be the optimal result. The metric will be the pullback of the other. So we know this under some conditions, but in general, we don't have that result. This is similar to Tataro's unique continuation result. So beta and the normal derivative, this is called unique continuation from the boundary. So here you have beta equal to, in a part of the boundary here, is the normal derivative equal to 0. And you have the wave equation inside equal to 0. Does this implies beta equal to 0? In many situations, this is true, but not in general. Okay, so this, of course, is again, boundary value problems are much more difficult than the case when you have boundary because of the complicated behavior of the geodesics. They can reflect many times, and so on. Young talked about this, so let me just jump over this. And the way, this is the Westerveld equation in nonlinear acoustics. Again, boundary data F. This is the sound speed, and beta is a nonlinear parameter. This is a quasi-linear equation. Involves derivatives in the highest order term of nonlinearity here, p squared. And you can, by second order linearization, you can prove an identity. This is what we usually do, and we did for the Dirichlet to Neumann map. for the Calderon problem, we prove that if the Dirichlet to Neumann maps, then you have this identity equal to 0, where the UIs are solution of the equation. You remember from the first lecture. But these are different equations. So here, the difference is that you have the coefficient that you want to recover, and these are solutions to the linear wave equation, not the nonlinear. These three, so you have a lot of freedom in choosing this. In this case, we have a solution of the equation involving the coefficients that we want to determine. That's why the nonlinearity helps. You're doing second-order linearization. Here, we're taking two boundary data, epsilon 1 and epsilon 2, and you want to recover this beta, and we have all this information. Okay? And this is the forward, as Yang explained, the forward wave equation, and U0 is the backward wave equation. And by using Gaussian beams, as Yang explained, these are other types of solutions. Remember, solutions is the key for the inverse problems of this type. Then we share solutions concentrated near geodesics. Then you can extract some geodesic information about the beta times some weight. And this can be inverted. Remember, we talked about the geodesic transform before. We can invert it under some conditions on the sound speed. Yang talked about this, so I'm not going to. But there are these pictures. L is the size of the image, and lambda is the wavelength. And this is the shape Logan phantom, which is a benchmark used in medical imaging to see how your algorithm, we have an algorithm developed by Acosta, is one of the authors here, using by inverting this geodesic transform. Here. We have the integration because the solutions are concentrated near the geodesic. So you're multiplying here, so you get something constant, but you have to show this. That's what Yang showed, it had to be concentrated near the geodesic. So you get information about the integral of beta along the geodesic. That's why it's important to concentrate solutions near geodesics. And this is another picture. This case is the brain. Of course, when this is higher, the pictures are the resolution is much better. Okay, so let me talk about other problem. And I will also talk about Einstein's equation to finish this briefly because it's a very complicated system. But let me take a scalar equation that has a gradient nonlinearity. So this is the wave, before we talk A times U to the fourth, has a gradient nonlinearity. And here we're going to take the Neumann to Dirichlet map. So we know the normal derivative. The Neumann to Dirichlet, you send Neumann data to Dirichlet data. That's essentially equivalent. Sometimes technically one is easier than the other, but it's the same information. And this is assumed to be a quadratic form in C. It's called a null form, depending on X and U. So it's of this form, N0 of XC. This is independent of U. The C variable corresponds to the gradient. This is the gradient term, and this is the gradient square, plus higher order terms. And so the problem is you consider the Neumann to Dirichlet map. So Neumann to Dirichlet map. So you send, and this is to U at the, this is the normal derivative. There is a typo here. It's amazing how you don't see the typos when you're. So the Neumann to Dirichlet means you send the Neumann data to Dirichlet data. It's a boundary cross 0t cross n. This is partial data. We're only taking an open subset of the boundary. So the question is, can we determine the metric G and the quadratic terms from the Neumann to Dirichlet map? No, no, it is correct. Sorry, it is correct. I was misreading. It's the Neumann, the normal derivative to the solution. This is what I wrote here. Okay. So it's, again, the assumption is globally hyperbolic. And then the boundary is like time-like. And a strictly convex boundary again. So this is these are called null, and M is not null. This is not null. These are called null forms as they appear in wave maps. But this is a sort of a model. I think I mentioned it here somewhere. It's a simplified model of wave maps. Wave maps is a system of equations. An example for which this is satisfies an equation of this form. So you have some coefficient times some metric here, positive this metric G0 here, the Minkowski metric, say, applied to gradient U, gradient in all the variables plus a multiple U squares times dt U squared. This is a nonlinearity coming from this term here. So this complicates the nonlinearity.
Are you saying this is what the Einstein reduces
No. Einstein's equation, I will say, is a quasi-linear hyperbolic system. This is a scalar equation. This comes from wave maps, which are maps that satisfy the wave equation in Lorentzian coordinates. That's where, like a harmonic maps is the elliptic case. But they are it's a system of equations. It's more harmonic maps is more complicated. One open problem that I want to mention tomorrow is to consider harmonic mappings themselves, which is not so easy, but there you have. Wave maps. You have harmonic maps for the Laplace-Beltrami operator. For the elliptic problem, you have wave maps, which are very important in geometry and relativity for hyperbolic equations. But they are systems. Systems are more complicated. Einstein's equation is quite complicated. So we have a strictly convex boundary, and the theorem with Yang here, Yang-Chang, is that if you know the Neumann to Dirichlet map, you can recover the conformal class of the metric up to diffusion fields. The conformal class again comes because we recover the boundary light observation set. And you recover in this diamond figure, right, intersected with the interior. The diamond looks like this. So we're talking half of this is the boundary now. The diamond is like this. So we're taking this part. You can recover the metric there, of course, in the interior of the manifold. Yeah. So these are all the points. This is the diamond figure starting at all the points in this neighborhood of the boundary. So there are many such diamond sets depending on the points that we take. So you recover more information, the larger the neighborhood is. If you have the whole boundary, then you can recover everything. Okay. So you can also look at the local problem and so on. Once you have G, you can recover this eta 1 M up to null forms, meaning forms that vanishes when C is equal to 0. So this is the formula for the forms. N0, this is N1. There is a factor U here. This is the gradient of U, and this is the square. And it doesn't matter whether you have cut points or conjugate points. So geodesics can come together. The theorem is still valid. But this is for another conference. Okay, so now I'm not going to go through the details of the proof. It's quite complicated. But the ideas are the same. So now let me finish the wave equation part and then we're going to go to the elliptic problems by talking about Einstein's equation. And so I'm going to go to another file. Where is it? No, it's not this one, sorry. This is the, so I'm looking for 3. You see Clemson 3? Oh, there. Any questions? The reason why I explained the case U square first, because that's the simplest possible one in order to explain the ideas. The ideas are very, yes? You can do the other way around too. This is technically it's a little bit easier to consider this. Yeah. The same result. Yeah. In applications, usually answering your question, one looks at Neumann to Dirichlet map rather than Dirichlet to Neumann, because Dirichlet to Neumann, you lose one derivative. And then from Neumann to Dirichlet is the opposite. So, but it's the same, the results are the same for both. So this is the same, I just have this is what we just covered. But I finished, and now here I have Einstein's equation. Okay, so Einstein's equation is, describes the gravity in the universe. You have a Lorentzian manifold again. Again, here you cannot think about the Minkowski metric because, oh, sorry. Yeah. So this is called the Einstein tensor, and this is called the stress energy tensor. This is the energy, and this corresponds to how the universe is curving, okay, because of gravitation, because of this stress energy tensor that you have. The universe curves. And this is called the Einstein tensor. This involves a lot of geometry. So this is called the Ricci tensor. This is the inverse of the metric. The Ricci tensor is the trace of the sectional curvatures. The sectional curvatures are the curvature in two-dimensional planes. So the full tensor, the full curvature tensor is of fourth orders. And this is of second order. And then the scalar curvature is the trace of this tensor. Okay, so this is answering your question, Chaim. in the case, in vacuum, T is 0. Einstein's equation, this is the famous Einstein's equation equal to 0. But we're not going to assume vacuum. In wave map coordinates means you use wave maps. So these are coordinates that satisfies the wave equation, each component. Right? The Einstein's equation is a quasi-linear hyperbolic system. So there are two aspects of this. This is given by this. You can see it's a system. Here, this is the second derivative. The inverse, the metric is involved here. That's why it's quasi-linear. Plus a term here involving G and the derivative of G. Yes. These coordinates for this always exist. Yeah. This is a theorem of Choquet-Bruhat. Choquet-Bruhat was the first one who proved local existence for the solutions of the initial value problem for Einstein's equation. Not trivial at all. Okay, so of course locally, I mean, this is, but there is also a condition similar to in Maxwell equations, the divergence condition saying that the total energy of the universe is conserved. So the divergence is equal to 0. So this is another complication that you have to have that condition as well. So it's quite complicated. So we try, this is our first paper I mentioned here. You can take a look at the archive. It's in 2013. Was more than 100 pages and very hard to read. And Laurie helped us to clean it up. It's about 70 pages or something. But Einstein's equations are very complicated. These nonlinear geometrical optics that I explained to you for the case U squared is extremely complicated in the case of Einstein's equation. And then we couple it with, in order to have a stress energy tensor here, we couple it with what's called scalar fields. It satisfies this equation, the Klein-Gordon equation. So this is the source here. The stress energy tensor will depend on this phi and the metric G plus another source. And you give initial conditions for the metric to be G hat and phi hat, and which are C infinity smooth and satisfies as the equations, Einstein's equation with 0 sources. And the stress energy tensor in terms of G and phi is given in this form. And we have to have that the F1 and F2 are chosen so that the divergence condition is satisfied. And so you take again the same situation as we have earlier. You take a time-like geodesic, the world line of an observer. Suppose we know there everything. We know the neighborhood, we know the metric in this neighborhood. The scalar field, this is coupling it with scalar fields. These are called scalar fields. These are scalar, but the number of scalar fields that you need is chosen. And you have the source, has two parts, F1, the source for the Einstein's equation and the source for the scalar fields. The support of these sources is contained in this neighborhood. Again, those are the controllable part. And you have the divergence condition. This is very important. Then if we have this data set, this is what we know, determines uniquely the metric, not just the conformal class. So the original result with Lassas and Kurilev was that you can recover it up to conformal factor because we could determine the light observation set. But with Iran, we proved by looking at the strengths of the singularities a principal symbol, in other words, that you can actually recover the conformal factor. So you can recover the metric on this double cone, this diamond figure that we had previously. So that's the theorem. Proof the same as before. But of course, it's much more complicated. And so that finishes the part on nonlinear hyperbolic equations. So there is one basic idea here. There is only one idea, which is use the interaction of waves, which is interpreted as singularities, like we had before in the Gelfand problem. You look at singularities. Interaction of singularities to produce a new singularity that gives that comes back to the region of observation and gives information about the inverse problem. And all of these references here use this idea for different situations. Of course, I'm not saying these are easier, because the equations are different and complicated. Nonlinear elasticity is very complicated. Young-Mills is complicated. The equations, to handle the different equations is not easy, but the basic idea is the same. Okay. Any questions? So I want to go to nonlinear elliptic equations, the nonlinear analog of Calderon's problem. Okay, so another file. Is Clemson. We're in Clemson 4. Okay, so for nonlinear elliptic equations, the idea is the same, actually. But instead of looking at the interaction of waves, you look at higher order linearization. Okay, this is useful for the case where the linearization of the problem does not help. So considering the nonlinear part, considering second order linearization or higher order linearization helps to solve the nonlinear problem. I will explain why. Okay. So let me consider a simple example. Consider this semi-linear elliptic equation. So m is bigger than 1. So it's bigger or equal than 2. Q is sufficiently regular here. And you take a subset of the boundary, any subset of the boundary. Okay, so this can be arbitrarily small. And it takes F sufficiently regular. This is the Hölder space of order 2. Alpha is between 0 and 1. This is sufficiently small data. Don't worry about these technical aspects. Then the solution. Then you have a unique solution of the equation. The smallness comes again because you want to prove that there is a solution of this boundary problem. So you have here set gamma here, and we are solving this elliptic equation. Before nonlinear elliptic equation. Okay, but the data is only in an open subset of the boundary. So we define the partial Dirichlet to Neumann map. So we send lambda q of f restricted to gamma is the normal derivative of the solution restricted to gamma, where the support of F is also contained in this neighborhood. So this is partial data. So we have data only here. So there is, in this case, there is uniqueness, and there are stability estimates also. If this is the same, then the potentials are the same. So let me point out that this result for the linearization, so linearization, let me put it here. Linearization does not work because we don't know this result. Say, suppose you have Laplacian is an open problem. Also, this will be one of the open problems, but let me mention it already. I think I mentioned this in dimension bigger or equal than 3. In 2 dimensions, there are some results. You take Laplacian u plus qu, the linear problem, equal to 0 on omega, and u equal to, at the boundaries f. You have a subset of the boundary, and you take the Dirichlet, you make the measurements, the electrical measurements only on this subset of the boundary, and the F is supporting the same set. Oh, I'm writing in 2 pages, sorry. Can you read? Then it's not known. It's not known that you can recover Q. So the partial data problem has not been solved for the Calderon's problem or for the potential problem in dimension 3 or larger. Dimension 2 has been solved. So, but for the linear problem, non-linear problem like this, as long as you have a nonlinearity, then it's okay. As long as you start with u squared here or higher, then you can solve the problem. Okay, so let me explain how. So let me take m equal to 2 for simplicity again. Oh. How do you? But how do you move the page? Oh, let me move it this way. Okay. Yeah. Thank you. So we take a Laplacian u plus q times u squared. And again, the quadratic nonlinearity for simplicity. This applies to any m. So you do a second order linearization of the partial Dirichlet to Neumann map, and we get the following identity. This is exercise. The integral, suppose, again, this is equal, the Dirichlet to Neumann map, or denoted by n, I guess. The integral, again, q1 minus q2. And now you have u1, v1, v2, v3. You have 3. This is second order linearization. So you linearize the problem twice. Dx is equal to 0. But these are harmonic functions. So Laplacian of Vj is equal to 0. J equal to 1, 2, 3. And the support of the VJs is contained in gamma. Okay, so exercise show this identity is just again second order linearization. So let me recall here. Let me recall the case that we had before, the linear case. So the identity, and I think we showed this, lambda q1 equal to lambda q2. This is the Dirichlet-Neumann map. This implies integral q1 minus q2, u1, u2 equal to 0, but the ui's are solutions of the equation with the q. Okay. And then for this, we took CGO solutions. Of course, to construct CGO solutions for nonlinear equations will be very complicated, and actually I don't know how to do it. But the difference here is these are not solutions of the equation related with the potential, because we're linearizing around 0. 0 is a solution here. U equal to 0 is a solution. So we linearize second order linearization around 0. These are harmonic functions, right? Not related to Q1 and Q2. The complication is that the support is contained in gamma, right? It's contained on a piece of the boundary. Questions? I want to make the analog of the analogy between the two problems. It's always an identity that we have been able to prove. Remember, for the acoustic problem, is the beta. It's an identity for some solutions. Okay, and this is more analog. This one is more analogous to Calderon's. Calderon's computation that I did at the very beginning of the week. It looked like it was a long time ago, but I want to leave this here. Don't you have the feeling that it was a long time ago? Monday was a long time ago. What the hell am I doing with time? Okay, so Calderon, which has been the so this is for the linear problem, right? Linearize around, I did it for the conductivity, right? Around U equal to 0. Let me do it for the potential. The potential corresponds to Q equal to 0. And then you can prove the linearization is given by U V equal to 0, where U and V are harmonics. I did it for the conductivity. For the conductivity was the gradient U dot gradient V. But for the potential, is just this. You can check it. And then he took this. But these are harmonic also, because you're linearizing at Q equal to 0. This is the case Laplacian plus Q U equal to 0. So this is similar to similar to that. Q1 minus Q2 is the H, but here we have 3 solutions. Actually, we just need 2, but in this case, 3 happens, and then, but they are solutions, they are harmonic functions, but the support is contained in gamma. And there is a result. I'm so bad at these things. Can you see that? No. Okay, finally. There is a theorem so I'll finish with this.
Scaling.
So how do I know?
Here's the scaling.
Uh,
You are using 0 point.
Oh, yes, it should be. Okay. So there is a theorem which is due to Koenig-Shostrom. And myself is the following. So suppose you have a function which is orthogonal to the product of harmonic functions. Let gamma subset of the boundary, of course gamma non-empty, open subset. Then they are harmonic functions. And the support of U and V is contained at the boundary, is contained in gamma. This implies F equal to 0. So it's the same as Calderon's computation. Calderon, remember, was integral HU B equal to 0 for, these are harmonic functions. Then implies H equal to 0, but you don't have any condition on the support. These are harmonic functions with support on a piece of the boundary that can be very small in principle. Okay. So this involves, I'm not going to explain the proof of this, this involves analytic macrolocal analysis and so on. So it's more complicated. Okay, so now that you can finish the proof. So believe this. Questions?
What does the first order linear look like?
Sorry?
What does first order linear equation of this nonlinear problem look like?
Yeah, it's Laplacian U plus QU. That's, the equation is the same as the linear equation because it's around 0. So it's the same equation. So linearization does not help. You go to second order linearization. Yes? Sorry? Yeah, the same. You had to go to third order linearization. And for M, you had to go to mth order linearization. I only describe the case 2 because it's simpler, right? Otherwise, you get more products of. Okay. So using that theorem that I just wrote in the blackboard there, well, it's not a blackboard, it's in the screen. You don't need B3, so because these are contained in gamma, you get Q1 minus Q2, B3 is equal to 0. And therefore, this is, for every B3, which is harmonic, you just take a harmonic function which is non-zero. And this set is of measure 0 because it's harmonic function. Then we get Q1 equal to Q2 because they're sufficiently regular, and that's the proof. But the point is that because you are linearizing around 0, the products of things that we have here are solutions of at the linearization. So independent of Q1 minus Q2. That's the point. Okay, so that's why nonlinearity helps. Right? So you go to higher order linearization to do this. Questions? And we're going to continue with the elliptic problem in the afternoon. Yes. Sorry? All dimensions. This is true in all dimensions. However, in dimension 2, we have the linearized problem is true. I mean, the nonlinear problem is true. So let me, again, I'm doing the same thing. In dimension 2,
The scale is
I keep. So in dimension 2, it is in the notes, by the way, it's in the slides, the first slides. I didn't talk about this, but in the partial data problem is solved. So you take Laplacian minus Q, plus or minus QU equal to 0. And you consider again, the Dirichlet to Neumann map. So U at the boundary is F. Suppose the support this is the normal derivative, and you restrict it to an open subset of the boundary with the support of F contain gamma. I suppose you consider this, and you have this for all F supported in gamma implies Q1 equal to Q2. So this is a theorem with Immanuilov, myself, and Yamamoto. So the partial data problem in 2 dimensions is solved, so you don't need to go to just linearization, you can solve the problem. Yes? So if you have a Taylor series, you mean a power series, yeah, you solve first, you do second order linearization, then third order linearization. Second order will recover the square term, and then third order will recover the. Oh, no, that's a more difficult question. And actually, at this point, we don't know. This will be also an open problem. Suppose this assumes, it's a good question, assumes a priori that you have a 0, because we need 0, there is no linear term. In other words, Yishao is asking whether you can do Laplacian U, let's call it V, is not to confuse with the U plus Q times U squared, right? And at the moment, no. We're trying this right now, actually. The reason is that you have to look at now you have to look not just a harmonic function, but Laplacian plus V. When you do the second order linearization, you have some factor here. And that we need to take some CGO solutions or something like this. It gets much more complicated. We use very strongly this theorem that I mentioned before, that this is orthogonal. This theorem that if this is 0 and support of U at the boundary and B is contained in gamma, is only valid for harmonic functions. I mean, I should say we only know it for a harmonic function. We don't know it for when you add a linear term. It's a good problem for you. I will give you a lot of exercises for the summer. You solve any of the problems, you have a thesis if you are a graduate student.
hour break, we'll come back, 10:30, we're setting something up for that.
Huh?
So,
Oh,
we have the lecture notes up to 3, so.
yeah, I will send you the podcast. Yeah. Yeah. You want to send it around? Yeah, sure. Sure, of course.
For your privacy.
Yes, no problem.
Okay. So basic, whatever nonlinear terms you're adding, the well postness is always no issue since
For
you're,
F is small.
since you're taking a small unit. This one, but that's really small.
No,
Size is very, very small.
no, probably look for another one. I think it was here. Go to downloads. Look for Clemson. Yeah, that's
But that's really small size.
This is smaller file.
I think Gunther opened the one with parentheses 1. But that's even smaller.
That's a text file.
Oh, that's text file. Oh, sure. This one. I think that's what. Okay, that's also probably you don't have any pictures.
I don't have pictures.
Oh,
in
okay,
that
so
one. I don't know movies. It's a smaller file than the others.
So the parenthesis 1. What's the one?
Look at the two.
Look at 2. Look at 2 first. 2 is supposed to be newer.
Yeah, right.
Look at 2. Does it look okay?
Yeah, that's okay. Yeah, it's a smaller file.
And the 3 doesn't have the Einstein equation in it. Probably you modified after.
Yeah,
setting it.
modified. Yeah.
So
Yeah.
can you update?
Yeah, let me send you the correct file. I think that's.
Or you can. Oops.
I will revise them. And,
Sure.
yeah,
So I did 1, 2 look better following your lecture, but lecture 3, so Einstein talk and the reference were missing.
right. Yeah.